Hi guys. So what we're going to talk about today is the subject of inverse functions. This is a topic that you would have seen before as early as Algebra 1, but we're going to be looking at it from the perspective of calculus. So the inverse of a function we can think of as just being an operation that takes x and y on the graph of a function and flips the order. So when we think about a function, it's easy to get lost in the idea that a function is a graph, but really what a function is a relationship. So function f is a rule to take an input, x, to an output, y. And the set of all possible inputs is called the domain of f. So the set of allowable inputs is called the domain. And the set of outputs for that domain is called the range. So the usual letters that we use to designate these are D and R, unsurprisingly. So informally, what an inverse function does is undo whatever f does. So if f takes an input x and spits out an output y, then the inverse of f takes that output y value and sends it back to the input that it came from. So the points on the graph of f look like this, right? If y is equal to f of x, then the point x comma y is on the graph of f. If f inverse of y is equal to x, what you're saying is the point yx is on the graph of f inverse. So xy being on the graph of f is going to mean that yx is on the graph of f inverse. Now, it's not always clear when an inverse exists and where it doesn't, so we're going to get into that as we get deeper into this lesson. So let's be a little bit more formal here. So more formally, we can think of an inverse as a function. So the inverse of f is a function f inverse, so that f inverse of y is equal to x whenever f of x is equal to y. So the inverse for a function is built from a function. I have to have a function in place before I can write down what its inverse is. Okay? And this relationship that we talked about on the last slide in this one, the idea where you have y and x in the inverse associated with an x and y in the original function, what that means is we can actually write down graphically what it means to be an inverse. Okay? So graphically, if we have some function f that looks like this, so here's just some random f, okay? And I want to know what its inverse would look like. Well, the way I can think about that is any point x, y that occurs on the graph of f must get flipped in its relationship when I write down a graph of f inverse. So if fxy is on f, then it must be the case that yx is on f inverse. And what that means is that these functions are actually symmetric with each other, reflected across the line y equals x. So again, what I mean is if you pick any xy, you can go straight across this line, and the point yx should be on the same, should be on the graph of the inverse. Okay. Now, does every function have an inverse? Well, no, because there's a big restriction that we make on the idea of what an inverse is. So in math, we want functions to be what's called well-defined, which is to say that whenever I have an object involved in some computation that I'm doing in calculus, I need to make sure that it's unambiguous which inputs get sent to which outputs. And so there's a big demand that we make of things that we call inverses. So this is the big demand. the inverse of a function must be a function. So if you recall, the definition of a function is a graph or a rule that can't assign more than one y value to the same x. Okay? So here's an example of a function that does not have an inverse. If you wrote down the graph of y equals x squared on the domain from minus infinity to infinity, then the inverse function for that, well, if we're going to reflect it over the line y equals x, or we're going to take all of those points and we're going to switch the x and y coordinates, what you would get out is this function, or this graph, I guess I should say. And explicitly, this graph is not a function because it fails the vertical line test. That is to say, a single value of x gives rise to two different y values. So for this setup, y equals x squared does not have an inverse. And it doesn't have an inverse because each x value splits into two different y values. So this idea that we can look at a function f and determine whether or not it has an inverse by looking at the condition where, so you see here, like this graph, we know that its inverse can't be a function because as soon as you tip it over, the fact that you have 2 points that have the same y value, that's going to correspond to a single x getting two different y values down here, right? So this x right here is associated with this y, and this x is associated with the same y value. So when you flip two different x's mapping to one y, and you flip the result, or flip the point around, you're going to get one different x mapping to two different y's. Okay? So this is not something that we're going to allow. So we want to disallow this. And that means that we're going to have to come up with a way of determining whether or not functions have inverses. And also a method for cutting a function down so that we can find inverses. So as an example of making an inverse, I can actually take the graph of f of x is equal to x squared and chop it down in a way that what's left does have an inverse. So if I look at y equals x squared not on minus infinity to infinity, but from 0 to infinity instead, well, now every x value is attached to a unique y value. So when I flip the function over, I get a function. This turns out to be y equals square root of x, okay, on 0 to infinity. So the idea here is that because this function had one x going to each y, and there's no place where two different x's map to the same y, that's the sort of thing I can flip over, and the result is going to be a function. Okay? If you've ever wondered why in algebra, when you wrote down an equation that looked like y is equal to x squared, and then when you square rooted both sides, you had to use plus or minus, it's because there's no inverse. Squaring and square roots aren't really inverses. The square function, which looks like this, when you tip it over into its inverse, it actually has two different branches. Each one of these things is a function, but the top branch, that's positive square root of x, that's an inverse for this part of the parabola. And the bottom branch, which is negative the square root of x, that's an inverse for this part of the parabola. So the reason that the plus and minus comes in is because there's actually not an inverse. There's two different inverses depending on the domain that you're looking at. The condition that we need for a function to have an inverse, this idea that for each x there is just one y, so that we don't have two x's going to the same y, that's called one-to-one. So a function is going to be called one-to-one if I can cut out the case that two different x's are sent to the same y. So the situation I'm trying to avoid here is the situation where I have things like the parabola, where I have two different x values that are mapped to the same y value. Okay, so we want to avoid this. And the way we do that is we impose the condition that anything that appears in the range is mapped to by only one value of x. If y is in the range of f, implies that only one x in the domain has f of x is equal to y, then f is 1 to 1. Okay? A more formal way of writing this mathematically that you'll see in later classes is f of x is not equal to f of y whenever x is not equal to y for all x and y in the domain of f. Okay, so this is a condition that is used often to check whether or not a function is 1 to 1. So, in fact, we can check real quick, right? So, is y is equal to x squared on minus infinity to infinity 1 to 1? So let's actually check and see, using the definition, if y equals x squared is a 1 to 1 function. So what we need to happen is, if I have two different inputs, they must map to different outputs. So what I'm going to do is I'm going to start by assuming that the two outputs are the same, and I'm going to try to look and see if that forces the inputs to be the same. So let's assume that x1 squared is equal to x2 squared. Then x1 is equal to plus or minus the square root of x squared, which is plus or minus x2. So x1 could be plus or minus x2. Well, that does not force x1 and x2 to be equal to each other. They might be equal or they might not. So this means that y equals x squared is not 1 to 1, because we started by assuming that the output values were equal, and we showed that that does not force the input values to be equal, that there's two different input values that result in the same output values, and that's not a 1 to 1 function. Let's actually write down a more formal definition now of a function having an inverse, and what that inverse is, and some of its algebraic properties. So formally, we're going to let f be 1 to 1 on an interval AB with domain capital A and range capital B. So that's the setup. The 1 to 1-ness means that we're going to be able to say that f has an inverse. Then f inverse has domain B and range A, and is defined by f inverse of y is equal to x whenever f of x is equal to y. So it's an important point here that inverses switch the place of the domain in the range, and that should make sense. After all, if f is a function that takes the inputs, which are the domain, into the outputs, which are the range, and the inverse undoes that, then the outputs of f are the inputs for f inverse. So how can one find an inverse? So this is an exercise that you would have participated in at some point, probably in a pre-calculus class. And the general rule that we're going to use is going to be the switch and solve method, which still holds. It's not possible for every function. Sometimes you're just given a pair of functions. If you're given f and g, and you want to show their inverses, then you need to check that f of g of x is equal to x for all x. That is, functions are inverses if one of the functions undoes the other one. So if it's the case that applying f to g just gets you back the original output again, then f undid g, and f is the inverse of g. Well, suppose that you're not given the inverses. You're just given an f. How do you find a potential candidate for f inverse? So step one is that you're going to write y is equal to some function of x. So whatever the function is, you need to set it equal to y. Step two is you solve for x. Now you should recognize right there that that means that there's a lot of functions that you're just not going to be able to compute the inverse of, because there are functions that involve trigonometric functions or trigonometric identities, where if you've got mixtures of polynomials and trig functions, those are usually not possible to undo algebraically. They're called transcendental equations. Step three, if you can do step two, if you can find x in terms of y, is to switch x and y to get f inverse of x. That is, that gives us a function definition for the inverse. So let's look at an example. Suppose that I'm given the function f of x is equal to the square root of x minus 2. Okay? Now, if I'm working with inverses, it's important that I always write down my domain and my range, because the domain and the range of the inverse are going to be determined by the domain and the range of the function I start with. So for f of x is equal to the square root of x minus 2, let's see, so that graph looks like this. I can't put anything inside that's smaller than 2, or I get a negative number, and we're not working in complex analysis, and so we don't take square roots of negative numbers. What that means is that the domain of this function is every number from 2 up to infinity. And the range of this function is all y values starting at 0 and running to infinity. You can see that because the graph here starts at 2 and then runs off this way to infinity. Well, that's the domain, is the possible x values. And the possible y values start here at the x-axis and then go up forever. And that's why we get this 0 to infinity for the range. So let's actually find the inverse using the procedure that we laid out. So what we're going to do is we're going to write down the rule y is equal to the square root of x minus 2. I have to have y's involved before I can do this. Step 2 is we're going to solve for y. So we square both sides and we get y squared is equal to x minus 2. And then we can add 2 to both sides to get y squared plus 2 is equal to x. And the final step here is going to be to switch the role of x and y so that we get f inverse of x is equal to y, which equals to x squared plus 2. So in this equation, what we've done to get the last step is we switch x and y. Because if we don't do that, we're still looking at the original function. It's actually the swap of the x and the y variables that gives us the inverse. Okay? Okay, now I'm not finished, because when I specify a function, it's not just enough to specify the rule, I have to tell you the domain. So the original function had a domain from 2 to infinity, and a range from 0 to infinity. And that means our new function has a domain from 0 to infinity and a range from 2 to infinity. It's the swap of the domain and range of the original function. So that's actually pretty easy to understand if you look at a graph of what the inverse looks like. X squared plus 2 is a parabola that starts at 2 and goes up. So notice first, those things are symmetric across the line y equals x. The second thing is it's only half of the parabola because I only was working with the square root function. And since the square root was 1 to 1, it's only that branch that gets reflected over into the half a parabola that represents its inverse. So now we're ready to talk about how calculus interacts with all of this. The big thing that we're going to be looking at is the behavior of derivatives and inverses, because that's actually very straightforward to look at graphically, although it's a little complicated to work out computationally what that should be. The first big question I've got when I'm working with a new family of functions like inverses is what properties do they inherit from the function they came from? So I can only do calculus on functions that are at least continuous, and I can only take derivatives for functions that are differentiable. So my hope is that if f is continuous, then its inverse is continuous. And if f is differentiable, then its inverse is differentiable. And both of those properties turn out to be true. So the first theorem says that if f is continuous, then its inverse is. If f is continuous on some interval from a to b, and f is 1 to 1, then f inverse is continuous on f of ab. And by f of ab, you should understand that to mean the range of f on the domain ab. So those are technical conditions to make sure all the math works, but the basic idea is that if f is a continuous function, then its inverse is a continuous function. Okay? The one-to-oneness guarantees that the inverse exists. The continuity is the property that we carry from f to its inverse. We get more, which is to say that we also get that f is differentiable and 1-to-1 is going to apply that f inverse is differentiable as well. And we get a formula for computing those derivatives where we don't even need to know the inverse in order to compute the derivatives. That's the power of this formula. So theorem 2 says the following. If f is 1-to-1 and differentiable, then f inverse is also differentiable. And you get this weird looking formula, f inverse prime of a, that is the slope of f, the graph of f inverse at a, is equal to 1 over the slope of f prime evaluated at f inverse of a. This is a strange looking formula, but it's actually easy to justify if you look at what the graphs imply about the slopes of f and f prime. So before I show you how to prove this formula, I'm going to give you an idea of where it comes from. So let's actually think about what this would say in a graph. So you've got some function f of x. And let's suppose that it's 1-to-1, and so it's invertible. So we'll reflect the graph over the line y equals x to get f inverse. And let's look at what the derivative should be at a particular point. So let's suppose that point right there is xy. So the derivative there looks like this. And the slope of that tangent line is equal to f prime of x. That's what the derivative does. It tells you the slopes of tangent lines. What's the slope of the corresponding point on the inverse graph? So if you come up here to the point yx, and you compute the tangent line there, it looks like this. And it's not hard to see that because slope is change in y over change in x, so slope is equal to delta y over delta x. If you switch the roles of x and y, and that's what happens in an inverse, then you actually get the reciprocal slope. So the slope of the inverse function at the point yx, because you flip the roles of x and y, that's going to be equal to the reciprocal of the slope of f at xy. And that's what that formula means. If we go back and look at the formula, what we're saying here is that if I evaluate the slope of the inverse function at a point A, that's the reciprocal of the slope of f evaluated at the other coordinate of that same point. Because remember, the x and the y is flipped, right? So A is a point in the range of f. So f inverse of A is a point in the domain of f. And so that's all this formula is really encoding, is the fact that when you look at this graph, that this tangent line and this one have reciprocal slopes. And all of the notational bulk just comes from having to transform the point xy into the point yx in a computationally consistent way. Okay, so for those of you that are interested, I'm going to write down a proof of this. So this proof is not required, but if you're interested in the way that mathematics is going to look going forward, if you're a math major, you might actually want to look at this because we're going to use some properties of f in order to show this. So what is the formula we're trying to show? We're trying to show that f inverse prime at A is equal to 1 over f prime of f inverse at A. So the first thing we're going to do is we're going to set up a bunch of substitutions that we can make just by looking at the definitions of f and f inverse. So I know that if f inverse of A is equal to B, that anytime I see A, I could write it as f of B because we get the opposite relationship that f of B must be equal to A. That's what it means to have an inverse relationship. The same relationship holds in this way. If f inverse of x is equal to y, then it must be the case that f of y is equal to x. So this is going to be the basis for our substitution. And what we're going to do is we're going to write down the definition of the derivative. So I don't know if you guys remember this, but the definition of the derivative is a difference quotient with a limit in it. So f inverse prime evaluated at A can be written as the limit as x goes to A of f inverse of x minus f inverse of A divided by x minus A. Now I know that this expression makes sense because f was continuous, which means that these limits all make sense. Since f was continuous, f inverse is continuous, and f inverse being continuous means I can actually do this. So now I'm going to do some substitution. What could I replace f inverse of x with? Well, f inverse of x is a y value, and that y value has the property that f of y is equal to x. So I'm just going to call that point y. What is f inverse of A? Well, I've called that point B. What is x? Well, remember that if f inverse of x is equal to y, then it must be the case that f of y was equal to x. So I can take out this x and I can substitute in an f of y. If f inverse of A, or sorry, if A has the property that f inverse of A is equal to B, then it must be the case that A is equal to f of B. And now the limit isn't x going to A anymore, because x tending to A, well, the x value going to A on the graph is the same thing as y going to B on the same graph. So that change in limit is guaranteed to make sense because both of the functions in question are continuous. And as long as everything is continuous, I can slide limits inside and outside of functions. Okay, that's the whole point of continuity. So then the last step here is to just write, well, this is the same as the limit as y goes to B of 1 over f of y minus f of b over y minus b, but this is just an expression that's a difference quotient about f. So this entire expression, after I apply the limit, turns into 1 over f prime of b. It's the definition of f prime of b. But what is b? B is f inverse of a, and we arrive at our final formula, 1 over f prime of f inverse of a. And this sort of argument here that we've used where we say, oh, these limits make sense, and I can switch back and forth from x to y because both f and f inverse are continuous, which means that it's okay to push limits inside the functions. And then to do the sort of substitutions we did here, all of this is sort of the heart of a type of math called analysis, which if you get into later math courses, you'll see quite a bit of. So that's a little bit of a heavy load, but it's important that you recognize that at the bottom of this, it's just geometry, right? All we've really done with this idea of computing the derivatives of inverses is just noticing a relationship that must exist on the graph of the two functions. The other thing that I should point out is there's a condition I missed in one of the slides that I wrote down, which is, notice in this graph, or in this setup right here, that we have a function that's on the bottom, right? We have this calculation of the derivative of f at the bottom. So we have to be careful that that's never equal to 0. So we actually have to impose the condition if f prime of f inverse of a is not 0. Okay, because if we don't, we could have 1 divided by 0 and things blow up. What that corresponds to is points where you have flat slope on a function turn into vertical tangent lines on the inverse. Okay, because that's what happens when you switch f and y, right? Since the slopes are reciprocal, a slope 0 turns into a slope infinity. And that's something that you need to avoid when you're computing values. With that said, the next video is going to consist of computing the examples, some from the text. With what we've built here, we're going to be able to build out a definition of the natural log that we'll use to construct E. So these are sort of the fundamental functions of calculus, and so I'm looking forward to doing that. All right, see you guys in the next video.